cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
I have an absolute treat for you. Or maybe it's just a treat for me. Well, I guarantee I am super excited for this discussion. Why? Well, because I'm going to have my past graduate supervisor, mentor, and friend on for this episode. Dr. Glyn Williams-Jones, professor at Fraser University in the Department of Earth Sciences. So that means back towards volcanology. This one and the next one, it's almost a two-parter. 2 episodes, 2 different guests, approximately the same location, and a great way to start the year. Usually, my guest and I's backstory is pretty simple. I poke someone by email, they say yes, or they redirect me to someone else who says yes. The 2 exceptions, no surprise, have been the episodes that sit squarely in my geological wheelhouse. I think because there's a colorful story here, I'll dig into a little bit of the backstory before getting into the science. So I came out of my bachelor's with a combined major in physics and geology, because why choose between rocks and hard places? Also dreams of studying volcanoes, poking lava with a stick. I wasn't a straight A student. I mean, I wasn't a bad student either. I was just, somewhere in the middle. Not exactly the kind that just grabs a committee's attention. So I headed north, literally. It's a cliche that young people go backpacking and see the world when they're young. I guess I did the same, although I traded culture for mosquitoes, caribou, and bears. I used my parents' address as a fixed address while I bounced around Canada's remote regions collecting geophysical data. When you're in the middle of nowhere, there's no rent, no groceries, no distractions. I saved up a pile of money and managed to volunteer at the Hawaiian Volcano Observatory. Between the degree and the previous 3-month co-op stint at the Hawaiian Volcano Observatory and experience working in hazardous environments in Canada, I managed to get in. I even spent a night camping on the erupting vent of Pu'u'o, which for a volcanologist is basically the equivalent of a front row seat at the universe's biggest concert. Along the way, I met retiring Professor Dr. Al Edgars, who picked up the work from a former student who had tragically passed away. I must have made some kind of impression because he connected me directly with my future supervisor. And that was that. Instead of how I met your mother, how I met my PhD supervisor? Luckily, that's not what we tuned into today. Today's topic, Mount Meager. A volcano in British Columbia, Canada that shares a surprising amount of overlap with Mount Baker and even Mount St. Helens. It's a Cascade volcano. Full stop. And no, the Cascade Arc doesn't politely end at the Canadian-U.S. border. Subduction zones don't carry passports, and as we've covered here on Whimsical Wavelengths before, this is where dense oceanic crust is sinking beneath North America, releasing volatiles into the mantle, lowering the melting point of the mantle above, and creating magma that eventually pushes its way up towards the surface. If you need a refresher, have a listen to the first episode of the season all about Messiah Volcano and basaltic Plinian eruptions. It's a blast. Literally. So this is kind of a 2-parter, and the second will be something completely different with a different guest, but same rough location. Listeners, please welcome Professor at Fraser University in the Department of Earth Sciences, my past PhD supervisor, Dr. Glyn Williams-Jones.
Hey there. Well, I'm glad to join you today.
It's about time. I mean, normally on academic resumes and application packages, it's standard, normal to have your past PhD supervisor as a reference. Why is that? And what does that say about Whimsical Wavelengths not having you on until now?
Well, I guess some people like to say it's all about the academic pedigree, but yeah, really it's more about, what you get on and go and do with things. So, you are missing out that the first episode of Whimsical Wavelengths was in my basement. So I was in there serendipitously.
I think technically it was like the third or fourth, but
or whatever. But yeah, no, I think for most of us, the key thing is, as a supervisor, is like being a proud parent, what does your former students go on and move on to and do bigger and better things?
I was more thinking more of like a sausage making of science thing, because if you don't have your PhD supervisor on your application to say to become a professor for a job, like that's usually a red flag, isn't it?
I mean, it would raise a flag, potentially. People would ask why, and then you'd have to have some difficult conversation as to why. But, my dad said a PhD, it's just a driver's license. It's a degree to go on and do your thing, do what you need to do.
Okay, this
And
is
it's better
totally...
that than piled higher than deeper.
Now this is kind of like we're really getting in deep. So your dad is actually a professor at McGill University, emeritus now, right?
Nope,
And
he's still fully active
fully active and producing more papers now than
he ever has. It's insane.
But that's not why we got you on here. But that's what happens when you start chatting, especially to an old friend who we still drink beer on regular occasions and lament about how we're going to take over the world with science. I'm not sure who's Pinky and who's the brain.
Global domination, it's where we're at.
So we're here for me to ask you questions about a volcano that I love dearly and is absolutely gorgeous. The Canadian volcano Mount Meager. So many different ways to tell this story. It's also been framed the most dangerous Canadian volcano. Implies we have lots of them? I mean, we're not known for them, so why is Mount Meager dangerous and how many do we actually have?
So we've got lots. The challenge, why is Meager dangerous? Well, and that's the bigger issue for most of our volcanoes, is because we know very little about them. They're fairly remote, they're hard to get to, and we've not had a big eruption in any eruption in living memory. And so getting people to be thinking about it, aware, is a challenge. And that awareness is also funding to go out and do the work. But Meager it's 60 kilometers northwest of Pemberton, about 150, 160 kilometers northwest of Vancouver. So it's a bit remote, but nevertheless, the communities are at risk. And it's the site of Canada's most recent explosive eruption, only 2,400 years ago.
So by lots, though, like, are we talking all of our volcanoes are like Yellowstone? They're like Kilauea? Where are we going here? Because no one really talks about volcanoes in Canada.
Yeah, we don't talk about volcanoes. We've got students in my group have been doing some research on that, trying to better understand the perception issue. We've got, you could certainly say, hundreds, but the issue is that, again, they're not overly active in terms of the time frame, and British Columbia being a very young part of the country, those observations are sort of lacking. We haven't had our Mount St. Helens eruption to be front and center, but we have volcanoes that run the gambit from small little innocuous cinder cones that you might see in Mexico through to big volcanic complexes, Mount Edzaiza up north, and now, again, very close to home, Mount Meager, Mount Cayley, Mount Garibaldi. And those are of concern because they are closest to population centers and infrastructure. So highways and pipelines and electricity corridors, these are important aspects that we have to consider.
All right, so let's dive into the 2,400.
2,400 years ago.
Yeah, the last eruption of Mount Meager, mainly because it's the one I know best. But how, when, why? Like, what happened?
Yeah, and it's a cool story, which is like so much in real estate, it's location, location, location. So we have this large mountain of multiple overlapping volcanoes built up over about the last 2 million years of activity. But 2,400 years ago, there was an eruption. Again, think visually on the scale of a Mount St. Helens style event. So there was a big ash column jetted up into the air. We think on the order of maybe 15 to 20 kilometers high, and it was big enough that it sent ash all the way out to Calgary, just on the outskirts of Calgary. So we're looking, 500 kilometers to the east. So we had this big explosion, and it rained down sort of things like tephra, but specifically pumice, what you have in the bathroom to work on those bunions. Well, up to 80 meters of this material built up around the volcano. And then subsequently, the eruption actually changed. And it went from an explosive eruption into what we call an effusive eruption. So lava flows coming out of the side of the volcano.
But that's not abnormal, isn't it? Like Mount St. Helens did the same thing.
Yeah, exactly. So it's not abnormal. But also the key thing is that those lava flows are not like Hawaii. They're more like Mount St. Helens, much more sticky and viscous because of their composition. And that lava flow tried to come out onto the side of the volcano. We're still not certain whether we would classify it as a flow or as a dome. Think about sticky toothpaste coming out the side, but it's hot. It's maybe 900 degrees Celsius. It's pushing out onto a steep slope, and then eventually it can't. Gravity is at work, and it's pulling down on that dome, and it breaks apart. And it breaks apart and flows down the flank of that volcano into the upper Lillooet River Valley. The flow is what we call a pyroclastic density current, or what used to be called pyroclastic flows. And this specific type is what's called a block and ash flow. So there were huge fragments on the order of, car-sized blocks of this lava surrounded by pulverized blocks of the same lava, just fine ash. And what's so cool is that pyroclastic flow flowed down into the river valley, couldn't go anywhere, and so it bulked up and built up a dam of material 110 meters high and about 3 kilometers wide. And because it couldn't go anywhere and because it was still hot, it basically melted itself back together again. It welded to form this essentially impermeable dam.
Wow. And you can see this, actually.
Yep.
As well as SFU and UBC, I guess you guys often do this field trip together. So if you're taking fourth year volcanology at SFU, and I suggest you do it if you're at all interested, you can go and see these cliffs that the river has cut down. And it's quite amazing because you see these clasts or these broken bits in finer grained matrix, gray matrix and black clasts. And I think the most special thing of all is what you can find downstream.
Yeah, because what's cool, the volcano products dammed the river. And this is a sizable river, the Lillooet.
Yeah, it's not small. It's not huge, but it's not small.
It's not small, but it's not huge. And it ended up forming a lake behind that dam of up to a half cubic kilometer of water. So the river is building up. It's got nowhere to go. It forms this huge lake. And then that lake overtops the dam, and we get a catastrophic outburst flood. We use the term Jökulhlaups, is the Icelandic term, because we see these events so often in Iceland. But it bursts out, and then thanks to work by my friend and colleague at UBC, Kelly Russell, and his team of graduate students and researchers, they suggest that this whole thing unzipped 2.5 kilometers of that 3 kilometers of dam, unzipped backwards in maybe as little as 8 hours, which is absolutely mind-blowing. And now what we see, if you stand on the remnants, on the leftover part, what's called Keyhole Falls, you can see this tiny little slot canyon that has formed over the last 2,400 years of erosion, and this amazing valley just opening up in front of your eyes. But downstream, as you mentioned, we can see these blocks of, sort of, say, 1 meter to 3-4 meters in diameter blocks in the deposits from that outburst flood. And what's so cool, it's these welded blocks of really glassy, fragmental material that have then are rounded just as they've been transported, but you can see all of these what we call cooling joints, and they're radial, so they come from the outer edges cooling in, and that tells us that that dam was still hot when it failed catastrophically because the cooling joints tell us about that process. So it's this amazing detective story to figure out the sequence of events, and history has a tendency to repeat itself. So in 2010, big landslide dammed the river, and lo and behold, we had another event. Not of the same scale, but it's a concern.
Yeah, I think for listeners following along, I think the best way, if you're at all geology curious, you've probably already seen columnar joints with basalt due to it just cooling from the top. And that's essentially what this is, although it's not basalt. You can still get these types of jointing in other lava flows, not just basalt. And then one of the more important things that I'll always remember Professor Kelly Russell for is that the columns never lie. They always tell you the direction of cooling. And so if you ever see those images, and I've seen lots of people say they're AI, most of them are not anyway, where you have these radial joints, they almost look like a fan. And that's because the cooling surface was rounded. And so it's always pointing back to where it was cooling from. In this case, usually it's due to glaciers. In this time, you have this hot clast being rafted out in this amazing flood, huge giant flood. And so now the cooling surface is all around the clast, and that's why you get these radial joints. Just so phenomenal. I always get a kick out of seeing those things.
The rule of thumb is that that joint is always perpendicular to the cooling surface. So if the cooling surface is changing, then your joint is going to change and rotate. And so, that's one of the really also the neat things. It wasn't the case 2,400 years ago, but in Western Canada, where we've had glaciations, you see so many of these different features where, you've had lavas come into contact with glaciers. And in fact, just a little bit to the south near Whistler, there's some amazing lava flows that we think are like lava eskers that flowed into either beneath glaciers or maybe even to glacial crevasses. And you can see these incredible changes in orientation of those joints and the sizes of those joints. So some really neat stuff.
Okay, so the last eruption, about 2,400 years ago, was smaller but similar to Mount St. Helens' 1980 eruption. Its dome, instead of being in a central crater, was off to the side of a hillside, so it ended up being too steep, and eventually that dome failed, filled the valley, created a lake, which then overtopped and broke that dam, that landslide, as I'll call it. And that was the last eruption. So what does the future hold for Mount Meager?
Well, and that's what we're trying to figure out, because one of the challenges in volcanology is trying to forecast the future. So what we always try to do then is, if you want to get a hint of what might be happening in the future, well, you look to the past. So some recent work with Kelly and his team, we were able to put some dates on some using isotopes on an earlier eruption about 24,000 years ago. And it was the same kind of eruption. It formed one of these block and ash flows. And in that case, 24,000 years ago, there were glaciers in that valley. So we're fairly certain that the flow went right across the top of the glacier, the valley glacier, and glued itself up onto the far side of the river valley. So we've got two eruptions that we have dates on. We need much better resolution. So in lacking that, some of the work that my team have done in the past is to take some scenarios and say, well, if we had an eruption in the future, if it was a little one, what could we expect? If it was a medium-sized one, could we expect? And if it was a Papa Bear, well, what would we look for? And so in all likelihood, a future reactivation of Meager would involve something similar, some kind of a probable dome growth, maybe because it is still capped with glaciers, although the glaciers are in pretty terrible shape because of changing climate. what we call phreatic eruptions. So steam bursts, if we've got heat coming up close to the surface, maybe some small, explosions if the system were to build up. But right now, we are in sort of a background level. There are hot springs at the base of the volcano. And a few years ago, working with some expert speleologists, expert ice cave, actually they work in cave search and rescue. They went into these ice caves where there's volcanic gases coming from Meager, and we're able to sample and measure those what we call fumaroles. So these volcanic vents. And the temperatures are about 90 degrees Celsius, which is sort of the boiling temperature at that elevation, about 2,000 meters, 2,200 meters. So it's low-level activity right now, but this mountain's being active for 2 million years. So looking forward, we've got to start monitoring the volcano, and that's a challenge.
Okay, well, you've answered kind of my whole question about the next thing, but it does bring up another important kind of suggestion, because I know every once in a while you'll see Mount Meager kind of in the local news, obviously not the international news because it's not erupting, with something like, oh my gosh, we found another vent, is it getting active type thing, only locally, only through journalism. But I guess that comes down to the fact that we just don't monitor it very well, hey?
Nope. At the moment, the only monitoring that we have, there's sort of two things. We have one station up on a ridge looking at what's called Job Glacier. And this is where there are these basically ice caves that have been formed by the volcanic gases melting away, and also the glacier thinning because of warming climate. So that's one station. We've got a couple of cameras and a small seismometer. That's not very effective. We have, thankfully, satellite monitoring now in place. Natural Resources Canada are using a special type of radar satellite monitoring to look for changes in surface deformation. So
and that's InSAR?
InSAR.
Yeah.
Yeah.
Just for the listeners, that's where you take a couple of pictures and you compare the two pictures, and then you're looking for phase difference from a laser essentially bouncing off. I'm simplifying a lot, but you're looking for a difference in the length, distance between the two satellite images there. And it can be accurate down to, it depends on how you do it, but it can be about half a centimeter.
Yep. And especially if you keep measuring over time and get repeat measurements, then you can start. It's challenging in Canada because of forests, because of steep slopes, all sorts of things. But that's now a semi-routine monitoring system. But beyond that, as with any kind of volcano monitoring, we never rely on just one technique. We want to have multiple layered approaches. And so we really need to have on-the-ground seismometers. And that's really the challenge, to measure the tiny earthquakes that might be generated by movement of magma, changes in the hot hydrothermal fluids that are within the volcano. And the more important thing right now, given Meager's sort of non-volcanic activity, is the landslides. It is the site of Canada's largest ever landslide in 2010. And so there are, again, former work by one of our former research students here identified at least 25 slopes on the volcano massif that are moving. And this is because the volcano is altered, and so there's unstable ground there. So we're trying to understand those areas and better map them, but we need to be monitoring that. So that's what we're hoping to start to be building out this coming summer, in fact.
You talk too fast, Glyn.
Okay.
Yeah, I'm joking. I just didn't get a chance to get in there with another question.
Yeah.
Because now I want to move on to the actual landslides, but I still feel like I need to go back. You did mention there was one seismometer currently there.
Yeah.
And I guess, is it close enough to be able to pick up tremor and that kind of stuff if it were to happen?
The little seismometer that we've got, it could, but because of its location, it's really too noisy.
Oh, okay.
So
That's what you mean by it's not a very good station when you
yeah,
mentioned it. It's just because
ground is not good.
yeah, look, listeners, sometimes you really want to make sure that your seismometer is directly installed into bedrock or something, because if you're into certain types of sediment, that sediment can shift. It can also pick up vibrations from wind a lot easier, and it can be a very noisy station if it's not right on bedrock or a good substrate. So that's, I guess, what we're talking about here. Although I did not know that, I'm just putting it together. But I really want to get into the landslides because
Yeah.
I think that is really the real danger probably in our lifetimes from this volcano, right? Like it's not, of course it could start getting the activity to erupt in the near future, but it's much more likely to fall down on us.
Yep. Yeah, absolutely. And so, the 2010 landslide is the largest in Canadian history. So, this was
Even bigger than the Hope Slide and the one on the
far bigger
Crow's
than that.
Nest?
Yeah. This was the recent work suggests it was 53 million cubic meters. So, that is about 20 times the volume of the pyramids, the Great Pyramids of Cheops. I didn't bother figuring out how many swimming pools that was. But, huge volume, absolutely huge volume. And that landslide came down on the south side of Mount Meager, went into a river there called Meager Creek, and then dammed the river. And so it forced evacuation of, I believe, 1,500 people downstream in the area, what's called Pemberton Meadows, and actually the village of Pemberton. And there is, continual movement on the whole massif because of landslide activity. That big 2010, it's so big, it's having long-term impacts on the downstream component because of flooding, because of the sediment moving down. But we know that it continues to have small rockfalls and landslides. And in fact, just 2 years ago, with our one sort of on-the-ground monitoring station and the two cameras, and this little seismometer that's not so good for volcano monitoring, we just, by good luck, picked up a rockfall that ended up, running the numbers, we figured it out, was about 200,000 cubic meters. So not as big by any means as the 2010 failure, but still a sizable event. And that was just above where the fumaroles are located. And so this rockfall actually turned into a debris flow. It scooted across the glacier and down the valley and didn't quite get far enough to enter the Lillooet River. But it just goes to show that these are major challenges for this volcano.
So why does it want to fall down though? Like, what makes it so hazardous? Because it's not every mountain tries to fall down on us all the time like this one does.
This one, it's because of its volcanic history. So this long-lived history, 2 million years of activity, 1.9 if you want to argue the details. But over that 2 million years, you've had all of these fluids. I mentioned sort of hydrothermal fluids, hot water coming around the magma at depth. And a lot of the time, these fluids are acidic. And so that those fluids and any acid gases are percolating their way through the mountain and altering that rock that typically is actually fairly strong, but turning it more into, like, essentially changing its chemistry into much weaker rock that is more like a clay. And so if you go out and dig in your garden, you can see how that clay, when it's compacted, could be, quite hard. But you get in there, you can smear it around with your fingers. So if now you've, over geologic time, turned these rocks into clay, or parts of it, then you've made it weaker. And then on top of it, we've got glaciers. So in the Canadian context, we've had long periods of glaciation, and the surface glaciers on the mountain are changing and interacting with the mountain and making it weaker. And so then it's just gravity.
Right. Okay, one more really hardcore science question. Because I mean, I kind of know the answer to it because I was your student. I would have been a poor student if I hadn't already had my own thoughts on this. But just not that long ago, something similar came out across kind of the science media where glaciers, the rapid removal of glacier ice, can cause or destabilize magma chambers because you're removing all that mass. And I already think I'm doing a better job of explaining it than some of the science media that I read. But if we have this very large edifice, or relatively large edifice, and it can have very large landslides, you're moving a lot of mass very, very quickly. Is that having a potential knock-on effect to the volcanic hazards as well?
It could. So in this case, the ice that is up there now is so thin that the change, if we just melted all of the ice off Mount Meager tomorrow, that change, the removing that weight is going to be actually pretty minor in the scheme of things. If we were in Iceland and we had a kilometer or maybe 2 kilometers of ice and we removed that, all of a sudden, different situation. However, there is interesting work suggesting that if you remove those glaciers because of changing climate, because of warmer temperatures, there's a debuttressing effect in the sense that that glacier is helping support the slope. And again, there's still some details in there. How strong is that relationship? But one of the sort of thought experiments that we're quite interested in looking into is to say, if we had another really big landslide like the 2010, or maybe bigger still, it's in fact possible if the unfortunate dominoes lined up that you could lose, maybe something even 10 times larger in volume than the 2010 failure. If that were to happen, and this is where we need to do some sort of computer modeling, is that change, if you have a massive landslide, could that pressure change be enough to actually pull the cork, take the top off your pressure cooker, and trigger a volcanic eruption? So this is something, again, that a former PhD student had put out as a thought experiment, with some sort of advanced but still fairly sort of limited modeling. That's an area that we're quite interested in trying to further explore. What would it take? So it's in the case of Meager, just melting off the ice is not going to do it. But if we had a truly massive landslide, that might be enough. But we actually need to do the geophysical modeling and the numerical modeling to pin that down. And a lot of dominoes have to be lined up for that to happen. That magma would need to be primed and ready to go. But we know that there's lots of it down there. We don't have a good handle on the numbers, but it's there.
When you get the numbers, whoever does it needs to come back on the show.
Oh, yeah.
Because, you're going to be all over the media locally anyway once you come up with that paper. They're going to be asking you for all kinds of things.
Well, see, this is other dominoes that have to line up. I need to line up the right person and the right funding and then the right, modeling. And maybe we can basically show that actually this is not a problem. That the change would have to be so extreme as it's just incredibly unlikely.
Or be so close to eruption that the point is kind of moot.
Exactly.
It really doesn't matter. It was going to erupt anyway. It just triggers it.
Yeah.
Okay, so what about the average person? So we're all talking here science, and this is what we've kind of sort of dedicated our life, or at least large chunks of our life to. What about the average person living in BC or around these volcanoes? Are they recognize these hazards?
They are starting to recognize these hazards. And in fact, work by one of my recently graduated PhD students, Uyen Pan, has actually been out to try to explore. And in fact, you and I, we were both very much under this faulty assumption, that Canadians didn't know anything about volcanoes, that they didn't have. Well, in fact, Uyen's research suggests that, in fact, People broadly do understand that we've got volcanism because they understand the idea of plate tectonics and the ring of fire, but it's in getting into the subtleties of things like volcanic hazards. Are you dealing with a lava flow versus a pyroclastic density current versus ashfall? Those are details that still need more education. As a scientist, we know what the implications are, but there are some interesting challenges that UYN study. For example, when communicating with emergency managers, there's a misconception on the part of the emergency managers that the volcanologists will be able to provide long-term warning of an imminent event. And if we're not monitoring, we can't do that.
Even if we're monitoring, we may not be able to do that.
Exactly. So that's why there is this push to expand monitoring. And if all goes well, we will have our first monitoring site set up this coming summer. So it'll be a start. But that's only one site.
For sure. And just for listeners, like normally at a volcano that hasn't erupted in a very long time, you often get precursory activity for weeks or months ahead of time. Not years, but usually weeks and months as things become destabilized. But you can also have it erupt pretty quickly without a whole lot of precursory activity, like days to week. And that's not enough time for most, I would say, emergency managers to get fully up to steam of what's going to happen and how to deal with the situation, which is definitely a problem if they're just kind of assuming that the volcanologists they'll have time.
And in fact, in the ideal situation, a bare minimum to be monitoring a volcano that is potentially, that is active but not currently erupting, we should have at a bare minimum at least 6 seismometers around the volcano. At the moment, the only seismic network we have is focused on earthquake monitoring at the tectonic scale. So it's not sensitive enough. It's not sort of deployed in the appropriate fashion for volcano monitoring. So we don't even have one at this stage. But there are some situations. There was an eruption in Chile at the volcano called Calbuco, where they had seismometers around the volcano. They'd been monitoring it for many, many years, and the eruption happened so fast with almost very, very, very little seismic activity beforehand that they didn't detect it until a few hours before it erupted. So the locals felt it and self-evacuated. So even in the best scenario where you've got lots of monitoring, those volcanoes can pull some surprises. Each one's got its own personality. So every now and then there'll be a surprise. But if we're not monitoring, then we have no chance.
Yeah.
So that's where we have to be going, and we're taking baby steps, but we've got a way to go.
All right. So this is actually part 1 of a 2-part series, but you're not the star of the show for part 2. So I'm going to go out on a limb and see if you can give me a hook for the next episode.
So I think the next episode, what is so cool, it's about how do we manage these types of events? Because we're dealing with a natural event. You're not going to stop a volcanic eruption just like you won't stop a hurricane, but you can manage the impact. And so some of that is about monitoring, but other parts, especially in the case of Mount Meager, is how do you respond after the fact? And in the case of Mount Meager, where we've had this huge landslide in 2010, what can you do to minimize that impact? And some amazing work is being done in terms of nature-based solutions to try to reduce the cascading hazards of multiple events in a way that's sustainable, that's economically sustainable, and doesn't involve pouring billions of tons of concrete.
Yeah. Okay, so now is the time to, I guess, call out future work.
Yeah, future work. I mean, what we need to do in all of the Canadian volcanoes, but in volcanoes worldwide, is be able to better understand those precursor signals that you mentioned. And so there's really neat work that can be done using advanced AI techniques, machine learning. In Canada proper, we need to be doing more work to understand what has happened in the past as we start to monitor. And so some really neat work looking at the rocks from past eruptions and dialing in. Where did that magma go? How long did it sit there before it erupted? These kinds of things, while also doing the planning and the communication. And so, yes, we're fortunate to have, in fact, a recently funded grant that'll continue both expanding the monitoring at Meager over the next 4 to 5 years, but also seeing about how we go around really working collaboratively with communities who are potentially at risk from these natural hazards. And I think that's a really interesting area that hasn't had much work. So this is going to be fun.
More than anything, it's also going to be really important to get this work done.
Absolutely. Yeah.
Maybe that's why I was so drawn to natural hazards as a young kid, because I realized more than just being awesome about looking at volcanoes and poking lava with a stick is like some of the things that you learn have real world implications directly without even having to go into the nuance of it all, which is awesome.
And it's when I was a grad student working on Masaya volcano in Nicaragua, one of the key things was that realization, yes, I get to come down and I get to do exciting science and learn new things, but I'm not living next to this volcano and dealing with the day-to-day impacts of long-term volcanic activity. And so it's eye-opening. And so your point is really important. Can we help those people who are living next to volcanoes continue to live there, but in a safe way? And that means having plans, if there is an eruption, and having the ability to forecast that one may be imminent.
Yeah, so maybe this is you brought it up again, Messiah Volcano. That was the first episode of this season. I made you listen to it.
Yeah. Yeah, I know. It's fun.
Anything you want to add? You got to, and if you haven't listened to it and you've listened to this one, you got to go back and listen to that one.
Yeah.
I took a very high level kind of approach.
Yeah.
Glyn's like, I'm going to make my fourth years listen to it as kind of like a review.
Exactly.
So
I didn't put it on the exam though.
You didn't? Well, there's always next year.
But I think the key thing with the Messiah episode that you brought up that is really important is, when we're communicating to the broader public, there's this, oh yes, all basaltic volcanoes look like Kilauea. Well, of course they don't, because everyone is different. And the fact that a volcano like Messiah can have these incredibly large eruptions, like explosive eruptions, it's not just nice, passive, runny lava that is safe. These systems are far more complex than we initially thought. And so that's where the science is interesting. And again, why it's also so important to be communicating to the public that it's, the devil is in the details.
For sure. And part of the reason why this whole podcast got launched, it's not the only reason, was a brainchild of mine that we are still going to work on without getting too much in the details, but looking at very large runny type eruptions of basalt and how quickly they happen. How quickly can they inflate? How much gas do they produce? And I guess we're still looking at 3 to 4 years away from being able to do that work.
Yeah. Well, we'll have to be patient on that project, unfortunately.
Yeah, it sucks, but it is what it is.
Yeah,
and I honestly can't wait because
Yeah.
this entire feed, it'll be several episodes all at once, probably all about the same thing, hopefully at some point.
Yeah.
Maybe we'll even do like a before, middle, like before, during, and after. So that way you guys, the listeners, whenever we get around to it and the stars align, I'm pretty sure it'll happen though, can actually follow along the beginning, the middle, and the end of how one of these science projects actually come together. because I think that's a bit eye-opening for people that have just because life is life. It is. Not everyone can be a scientist. Not everyone can be able to go through one of these things and take them from start to finish. So I think it'll be an interesting project for you guys to listen to and for us to conduct.
Yeah, and I think that one take home is science, like so much in life, involves a lot of patience.
Oh gosh, yes. Backing to the Messiah episode again of picking crystals out of petri dishes. Yeah. Okay, but we're here at the most infamous part of every episode with a guest. Glyn, you have to tell us a science joke.
So I went hunting, and all of the volcano science jokes I thought they were kind of dumb.
And this is the only type of hunting you'll ever do, right?
I know, exactly. Yeah, except with a cat. But I thought, given the scope and the name of your podcast, I would go with this one. So, Photon walks into a hotel and asks for a room. The front desk attendant says, "Any luggage?" Photon replies, "Me? Nah, I'm traveling light."
Awesome. Well, I can almost guarantee that Glyn will be on again. So don't provide me too much hate because I'm bringing him on anyway. Thank you so much for doing this, Glyn.
My pleasure. This is fun.
And there it is, the first full episode of the new year out to your listening ears. Thanks so much for listening. If you haven't all yet, subscribe, poke me on social media, continue bringing in some of that amazing and good feedback. I need it. I need to know what listeners want and how that jives with where I want to take the show. I did get some listener feedback most recently, and I'm creating a solo episode just about that topic. It's amazing. You can have an effect on the show and what everybody else gets to hear. In the meantime, subscribe, tell a friend, you know the drill. See you in 2 weeks.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by. Her